geometric probability. Last class we talked about finding areas of different shapes, particularly sectors and lengths of arc lengths. Today we're going to talk about probability. Here is a rectangle of which part of the rectangle is shaded, and we need to find the probability. What do you think would be the probability if I was to drop a dart into this rectangle of landing in the shaded area? And they don't give you any information, but I think most of us can actually see that the probability would be 1/2, 50%, 0.5. For this unit, we're really going to use fractions for most of the answers. The probability of this rectangle of landing in the shaded area would be 2/3. The probability of landing in shaded areas would be 4 out of the total, which are 9 units, so it would be 4 out of 9. In general, probability P is the shaded area divided by the total area. Shaded area divided by the total area. Probability of a shaded area is the shaded area divided by the total area. So here are some examples, and we need to find the probability of the shaded area falling in the shaded area. So step 1 is to find the probability of the shaded area. To find the shaded area in general and divide it by the total area. Well, for this one, the total area is a little bit easier to find. The total area is the entire circle. What's the area of the entire circle? It would be the radius of the entire circle squared, pi r squared. So the radius is 10. The entire area of the figure is 100 pi. The shaded area would be the entire circle area minus the white part. Well, the white part is pi r squared also, which is 6 squared, which is 36 pi. 100 minus 36 is 64 pi. Now we can combine 100 pi and subtract 36 pi because they are like terms. So the shaded is 64 pi. So the probability of landing in the shaded would be 64 pi over pi, which can be simplified to 64 over 100, 32 out of 50, and you keep going until you get the easiest or the simplest. I think 16 over 25 is the final answer. Okay? Part B, find the probability of landing in the shaded area. Well, we need to find the shaded area, and let's see. This is supposed to be a semicircle. So can we find the area of the entire semicircle, the total area of the semicircle of radius, not 10, radius 5. The total area would be the area of an entire circle, which would be 5 squared, which is 25 pi. That's the entire circle, though, and because this is a semicircle, it would be 25 pi over 2, and this one, I think it's easier to do 12.5 pi. Now we have to find the area of the triangle. Well, because this is a isosceles right triangle, we can drop an altitude, and let's see. Oh, this is also a radius, isn't it? Straight up and down. So this would have to be 5, wouldn't it? Because this touches the circle. So the area of this triangle, the area of the shaded area, is 1/2 base times height. The base is 10 and the height is 5. So we get 25 for the shaded area. So the probability of landing in the shaded area is the shaded area over the total. But we can simplify the numbers so we can get 2, and then 12.5 becomes 1. So this would be 2 pi. And that would be the answer for B. So there's 2 more problems on this page. So you do these. Actually, C looks a lot like B, but the other part. And try D. Okay, so for D, I want to talk about D. Like the circle is inscribed in a trapezoid, and we would have to try to find what? This is an isosceles trapezoid, so we could actually find the height, this height, and this height. I'll get us started here. So this thing is 8 here, and you could find each of these pieces. So you could find this entire length here. And what is this entire length in relation to the circle? I would argue that the height of the trapezoid is also the diameter of this circle. So if you can find the height, you can find the radius, the diameter, and solve the problem. Okay? See you next class.